Okay, good morning. We want to,
Good morning, sir.
good morning, everyone. We want to continue our discussion on convolutional neural networks. And after that, we will look at backpropagation in slightly more detail. And then in the latter part, we plan to look at uh, so-called fine-tuning, that means taking an existing model and then getting it to work with our data, because large models mo cannot be trained quickly. Then after that, depending on the time that we have, we want to look at object detection also. And in particular, we will look at how this famous object detector YOLO works. So that's the plan for today. Yeah. So last time we studied this Linet 5 in detail. Actually, we understood what are the how many parameters are there and what are the sizes in the memory that is required to hold these structures. And also we did a very, close implementation of this in PyTorch. And we were able to train that using MNIST. Although I wanted to do CFAR10, the CFAR10 server in University of Toronto was not working, so we could not download that. But with MNIST, we were able to get that done. But when the dataset changes, you had to do some changes to the network because CFAR10 is for color images. Yeah. Okay, we start from here. So all these things were prior to the advent of ImageNet. Mm. ImageNet, as we discussed, was built by Professor Fei Fei Li and her student, and it has 14 million labeled images with 20,000 classes. But what became very popular is this ImageNet large-scale visual recognition challenge called ILSVRC with 1.2 million images and 1,000 classes. So in 2012, what happened was the so-called top 5 error that was about 26 suddenly became 16 due to this very important contribution called AlexNet. It's a landmark paper now. So written by Alex Kuczewski, Ilya Sutskever, and Professor Jeffrey Hinton. Mm. Professor Jeffrey Hinton, as you know, finally won the Nobel Prize. So we will study about AlexNet in a little bit of a detail. So now this is a picture of the AlexNet as it appeared in this famous paper called AlexNet paper, 2012 New Reefs paper. So it had, I think it received a 227 by 227 images, and it had two GPUs. So you can see the top GPU and the bottom GPU. So this is what the paper showed. So some part of the figure is not there. So it is similar to lineage that we studied, but max pooling was introduced and so-called ReLU nonlinearity rather than the hyperbolic tangent nonlinearity that was there in the Linet 5. And then 7 hidden layers and 5 convolutional layers and 3 fully connected layers, giving rise to 650,000 units and 60 million parameters. And 2 GPUs, 3 GB NVIDIA GPUs, GTX 580 cards, 50 times speed up in comparison with the CPU implementation. But these were written by CUDA by hand by C++ using C++ CUDA. So dropout regularization and GPU training, all these things came because of this AlexNet. Okay, so let's now this picture is slightly hard to study. So you can see it has the familiar concepts that we have. So 11 by 11 convolutions and the stride 4, and from that we can calculate the resulting tensor size is 55 by 55 and 48 convolution kernels and 48 convolution kernels, giving rise to 96 convolution kernel. So I'll give you a simplified picture. Now, this is a simplified picture that I took from this website. Now you can see there are 227 by 227 images and 11 by 11 convolutions And because stride is 4, we know how to compute the output size, right? Remember the output size computation. I'll maybe quickly show you that slide so that you know that we are looking at the same concepts again and again. Yeah. Yes, with this you can see how do you compute the output size, output tensor size, h prime, h minus k plus 2p divided by stride, right? And p is the padding, k is the kernel size, h is the height of the image, height of the width, plus 1. So this is the formula that we have to use. It's very simple. So you can see 227 minus 11, there's no padding, so divide by 4 plus 1, 55. So I think uh, I did not compute exactly. I hope you get 55 here. And there are 96 kernels, so that's why the number of channels is 96 in this output structure. Then so-called overlapping max pooling. So they had the 3 by 3 max pooling, but stride is 2. So therefore, you can compute the size of the output tensor. So it is 27 by 27. So we know that due to max pooling, the spatial size becomes smaller, especially because of this, because the stride is 2, spatial size becomes half in width and half in height. The number of channels remain the same. And there's another convolution. So that convolution is 5 by 5 convolutions, and padding is 2. So you can see 27 plus this is 2p and minus 5 divided by 1 plus 1 because the stride is 1. You get again 27 by 27 and so on. So finally, when you go, you will have a structure 6 times 6 times 256. So what that means is its size is, if you compute 6 times 6 times 256, you will get 9216. So this 9216 you flatten so that you get this 6 by 6 by 256 you flatten. So you get a 9216 nodes. Those nodes you fully connect to 4096. 4096. Those also you fully connect to 4096. And then finally 1000 because there are 1000 classes. And then you apply softmax on that, raising to e to the power and dividing by the sum of e to the powers. Uh, yeah. Okay, so now let's do a computation of the number of parameters and number of amount of memory used and the number of floating point operations that this network requires. So it is very important for us to be able to analyze these things because we have to know the amount of resources that we would need when we construct a neural network. So first of all, let's take the first convolution layer. So you know that these are hull images, so therefore input number of channels is 3. So height and width are 227. The number of convolution kernels is 96 as you saw, 48 in the top GPU, 48 in the bottom GPU, altogether 96. The kernel size is 11 by 11 and the stride is 4. There is no padding. So what is the output number of channels? Of course, it is the same thing that we are in here. It will be 96. And then height prime and width prime, the output size, spatial size of the output texture. So you have to apply that formula. We know the formula W minus K plus 2P divided by stride plus 1. So you can see these computations are quite easy to understand. 227 here. And because it is 11 by 11, K is 11 and 2 times P. So padding is 0. So therefore, it's here stride is 4. Because of that, the spatial size drastically becomes small. So you get to 55, 55 by 55. Yeah. Then we should compute the amount of memory required to hold this tensor in the computer's memory. So that we can compute by this, right? Number of kilobytes is number of elements times bytes per element, like how many bytes are required to hold this element. Of course, we know because these are the 2-bit floating point numbers, we need 4 bytes. And to convert to kilo, we will divide by 1024. So C out, that is our 96, and the spatial size is 56 by 56, 55 by 55. H and W are 55, and you multiply by 4 and divide by 1024. I mean, then you will get 1134 kilobytes. That's there. Okay. Then can you compute the number of parameters? Uh, how do you compute the number of parameters? to compute the number of parameters, you have to know the number of kernels that are there. So how many kernels are there? 96 kernels are there. And also we should know the size of each of these kernels. So size is 11 by 11, and we have the biases also. So it is very easy to do that. So parameters, weights plus biases. You can see the if you take each kernel, it is seen times k times k. Remember, when you think about a convolution kernel, although we are talking about the spatial size k by k, in this case 11 by 11, we must know that it spans the total number of input channels, like so, right? So here this C in, or the number of input channels, in this case is 3, because it is just a color image that is coming. So therefore you can see C in 3 times 11 by 11, and 96 is the output, and because for each of these kernels, we have to have a bias, so it is 96. So 34,944 parameters. So approximately 35,000. And then the number of floating point operations. So to compute the number of floating point operations, we have to consider the output structure, output tensor size. So the output tensor, uh, now we can see, is 55 times 55 that we computed. And how many channels are there? 96 channels, because we are running 96 kernels. So to compute each of these cells, like there are that many cells, 55 times 96 cells. To compute each of these cells here, each of these nodes in this, how many computations do you need? To compute that, you need to do a convolution operation, right? Convolution operation that will be placed at a particular location in the input structure, and the kernel size is, as you know, k times c in. So we have to multiply uh, k times c in to compute the amount of computation required to produce each cell in the output tensor. So therefore, total you can get by multiplying by the number of tensors. So there is this calculation here. So you can see, so number of output elements, that is this one, operations per element, because these convolutions are um, sorry, 11 by 11 convolutions. Uh, so 11 by 11 convolutions. And for a color image, so the depth is 3, right? Depth is 3. This is 3. So that's why you get this one. So I hope this is clear how to compute the number of floating point operations. Any questions about this? All right. Then we can move forward. We can now do the same for all other layers, but there is one thing, like pooling layer, right? Pooling layer. So input number of channels is from the previous one. So this is the input number of channels in the pooling layer. Of course, we know that the height and width are 55. So due to pooling, does the output number of channels change? No. So it will remain as 96. And the kernel, we have been given that in AlexNet they use a 3 by 3 kernel with stride 2. So we have to use the uh, formula for max pooling, and that formula is almost the same as the formula that we use for convolutions, w minus k plus 2p divided by s plus 1. So yeah, therefore you get 27.5, and you flow it to 27, and so therefore you get 27. Yeah. Okay, so therefore memory requirement and all sorts of things you can compute, but I will not compute them because we did that once. And pooling layers have no learnable parameters, so 0. So memory, number of flops, it's very small because you just have to do just comparison. So we will write 0 there, but you can exactly calculate if you want. So for the others, I will not do any computations, but you can do it by themselves, yourself. And you can see here 9,216. Uh, 9,216 is the number of elements that you have. If you think about this, 6 times 256. one. Uh, then because you have 9,216 elements, you can compute it like that. And 4096 is the output size. So here you can see it is 4096 somewhere I'll show you that diagram. In this diagram, you can see 9,216 to 4096. And because of that, you can compute the number of parameters that are required and so on. Yes. So 4096. And you can see the floating FT6 parameters, C in times C out plus C out. So that's how you compute the parameters in a fully connected layer or a linear layer. And then floating point operations, you have to do lot there, C in times C out. So this is what you get. So the similar pattern that we observed with Lenet, you will see. Yeah, here's the full computation. Uh, so if you ask how did they do this when they designed the AlexNet, how did they find the kernel sizes and so on? They did with extensive trial and error. But now people have some formulas or proper ways of doing that. So I'll give you a couple of minutes to focus on this. If you have any questions, please ask. So please do not hesitate to ask any questions because you are here. Then you can ask, and most of you I can answer any question. Okay, let's move forward. So if you analyze the memory usage, so from the previous table, we are plotting. So most of the memory usage is in the early convolution layers. What's the reason? Because then there the spatial size is large. So you can see that's a memory. And then nearly all parameters are in the fully connected layers because fully connected layers C in time C out. So many parameters there. In the convolution layers, the number of parameters is less. You can see, right? And then the computations, floating point computations are in the convolution layers. And in the latter layers, it's less. So this is the regular nature of a convolution. Okay. I hope everything is clear. Please don't hesitate to ask if you have any questions. All right, let's move forward. The 2013 winner is called Zeiler-Fergus network. So it is like the AlexNet, but slightly larger number of parameters, but we don't have to study. But this is an important one. The 2000, it's a 2015 ICLR paper. I don't remember when it won the challenge. Um, So they came up with some design rules. So these are VGG, Visual Geometric Group at Oxford University. All convolution layers are 3 by 3, stride 1, pad 1. Now that's easy, right? All max pools are 2 by 2, stride 2. After pooling, double the number of channels. So AlexNet had 5 convolutional layers. VGGNet has 5 convolutional stages. Stage 1, a conv pool. So you can see in the VGG16, This is called VG60 because it has 16 layers. You can see conf, pool, right? And then stage 2 also pool, pool. And you can see the number of channels get doubled as the after the pooling layer. Can you see that? 128 becomes 256. 256 becomes 512. But here the rule is slightly changed. Um, so you can see in the 19 version, VG19, which has 19 layers, there is an additional convolution layer in the stage 3, 4, and 5. So you can see that additional one over here. Yeah. So I think you can understand the structure of the VGGNet. Okay. So VGNet has much more parameters, consumes much more memory and floating point operations. Okay, so just to study this, why these 3 by 3 convolutions are okay, side one, pad one. So now let's consider a 5 by 5 convolution. If you do a 5 by 5 convolution from C channels to C channels, so you will have how many parameters? C squared times 25 parameters because input tends in number of channels is 5. So your convolutional kernel will be of size 5 times 5, and number of channels will be C, and you have 5 convolution kernels because it's C to C. So 5 times 5 times 5 times C. So that is 25 C squared. Yes. So if you take two 3 by 3 convolution kernels, 3 by 3 from C to C, 3 by 3 from C to C. So you can see 9C squared is the number of parameters in one of those convolution layers, and you have two of them, so 18C squared. Yeah. And the floating point operations also you can compute 25C squared versus 18C squared HW. So you can see two 3 by 3 convolutions have the say, I'm sorry, sorry about that. Uh, two 3 by 3 convolution kernels have the same receptive field as a single 5 by 5 convolution, but far few parameters and takes less computation. So you can see, so this is a 5 by 5 kernel, but the 3 by 3, two 3 by 3 kernels also have the same receptive field. So this is the advantage of using 3 by 3 convolutions, two of them in instead of one 5 by 5 convolution. So they found this, and now this is very commonly used. This is what we commonly use in convolutional neural networks. Okay. All max pools are 2 by 2 stride 2. After pool, double the number of channels. So these things I will not discuss too much. So you can at home look at this table. And as we looked at the previous table, uh, see, so you can see this doubling number of channels, all the things are there. Okay. So after that, in 2014, they came up with the GoogleNet. So this is also a good contribution. But some ideas are used from this, but not all ideas. Like they had a SIM network for aggressively downsampling of the input in AlexNet and VGG. Early layers were very expensive because of this reason. Quickly downsample. And then they had this so-called inception module. So they thought that to make a decision, they need the different kinds of receptive fields. So, for example, they wanted to first do a 1 by 1 convolution and then do a 3 by 3 convolution. Then 1 by 1 convolution, then do a 5 by 5 convolution. All this, then directly 1 by 1 convolution, then 3 by 3 convolution, then 1 by 1 convolution. So all these combinations they thought that are required. So I mean these concepts are not really thought about right now. And then there's thing called global average pooling. So we will discuss about that a little bit later. So the STEM network in the GoogleNet we will not study, but you have the capacity to study that because we did the AlexNet in slightly more detail. So this is the inception module. So I briefly described that. So from the previous layer, one by one, one convolution, one by one, followed by three by three, one by one, followed by three by five, three by three, followed by one by one. So local units with parallel branches, local structure repeated many times throughout the network. So one by one is a bottleneck, layers to reduce the number of channel dimensions before expense convolution. So we can revisit that when we think about the ResNet. So we'll briefly look at the global average pooling that was used in GoogleNet. No fully connected layers at the end because we know that the fully connected layers have so many computations. I'm sorry, so many parameters. Instead, use global average pooling to collapse spatial dimensions and one linear layer to produce class scores. So VGGNet, of course, had most parameters were in the fully connected layers. And now that is removed. So think about this now. They have 1024. So mm, and uh, seven spatial size is seven, and so you run a um, 7 by 7 kernel with stride one with 1024 kernels of those kernels like that. So when you do that, you get the output size as one by one. See, one by one. And of course, the number of channels is 1024. So this is a spatial collapsing operation. It's called global average pooling. So these things, this thing you use to classify. So then they had some auxiliary classifiers also. Only the reason for this is important. They had the so-called auxiliary classifiers because they could not get the gradient to backpropagate properly. Because this is a deep network, and by that time they did not know the so-called layer normalization. Normalization, I'm sorry, Bletch normalization had not been discovered by then. So therefore, they had problems in getting the gradient to backpropagate. Yeah. So in summary, ImageNet was introduced and ImageNet large-scale visual recognition challenge. And AlexNet had max pooling, relative nonlinearity, and large number of parameters. VGG, all convolutions are 3 by 3, stride 1, paired 1. All max pools are 2 by 2, stride 2. After pooling, double the number of channels. GoogleNet, they introduced a STEM network, inception module, and the global average pooling, and the auxiliary classifiers. So now we can study the ResNet. So before that, do you have any questions? Okay, then. Now let's study the concept of ResNet. It's a very important concept. So ResNet is also, I will show you a highly cited paper, highly cited paper. You can go to Google Scholar and see. So we can see AlexNet. AlexNet, search for Alex Kushevsky. That's AlexNet paper. Yeah, okay, let's look at I don't remember. ImageNet classification of deep convolutional networks. Do you want to search? That's one. This is that paper. 155,000 citations. You can see how important that paper is, right? And then the ResNet paper is also a very important paper. It's called residual networks. So you have to get exactly the correct name. So you cannot exactly find that. Let's look at it anyway. To show you that inside how important those things are. Deep residual networks for image recognition. So this one cited by 390,000 times, 319,000 times. So you can see how important these contributions are. Okay, so let's study this. And now something that you know is to run a neural network, we use gradient descent, some form of gradient descent. Uh, to do the gradient descent, what do we need? We need the gradient of the very end of the network's loss function, loss, with respect to the weights of the network, weights of the network. So this gradient that you compute at the very end of the network has to be back propagated. So we look at that in slightly more detail today. That uses the so-called chain rule. It's a function of a function of a function, that kind of a thing. So therefore, when you backpropagate the gradient, actually there is a tendency for the gradient to vanish. So this is the problem that ResNet solved. With batch normalization, also deeper models could be trained. Uh, uh, I totally lied to you. I totally lied to you. So with this so-called batch normalization, the vanishing of the gradient problem up to some extent could be solved. But still, they made this observation. ResNet people did this observation. Okay, let's understand that. I'm sorry about the mistake that I made. I was talking about batch normalization, not the ResNet. Deep models, the deeper model does worse than the shallow model. So let's see what that means. Now think about this, the number of iterations in 10,000s and the test error. So you can see they have taken a 20-layer network and a 56-layer network. Which one has the higher test error? 56-layer network. So 56-layer network does worse in the test error. But maybe this is okay. We can call this, it is overfitting. That means it may have performed well in the training phase, but did not perform well in the testing phase. That means it works well with the training set, not with the testing set. That means it has optimized too much for the training set. Okay, that's called overfitting. Yeah, but then what they observed was this. Even in the training phase, the 20-layer network had lower training error than the 56-layer network. So therefore, it is not an overfitting problem at all. So they thought about it and they gave some kind of a proof by construction. We will look at that. In fact, the deeper model seemed to be underfitting since it also performs worse than the shallow model on the training set. It actually is underfitting. 56-layer network has not been able to emulate the 20-layer network. Okay. A deeper model can emulate a shallow model, copy the layers from the shallow model, set the extra layers to identity. So, so I hope you understand this concept. Now you take the whatever 20-layer network that you have. So it has a certain error, no? So to this 20-layer network, okay, all these are weights that I'm representing, right? You connect additional 36 things, layers that just multiply by 1. Multiply by 1. These are identity layers. Just fix 36 of those identity layers, right? So the performance should be the same, no? Because we're just multiplying by 1 here. Thus, the deeper model should be able to do as good as the shallow model. So they hypothesize this is an optimization problem. Deeper models are harder to optimize, and in particular, don't learn the identity function to emulate shallow models. This is what they learn from this. So deeper models cannot emulate the shallow model. So as a solution, they chain the network so that it is very easy for the network to learn the identity functions. Yeah. So let's see what they did. So they took an input and the convolution layer, ReLU non-linearity convolution layer, and the output. Then they said, to make it easy for us to learn the identity function, they directly give the input. That is the identity, right? Directly give the input, nothing happens. Identity function. And then this will be there as an addition to that. So if you set all these to 0, your network, that means this one to 0, your network is just producing identity function. Your layer is just producing the identity function. So this is called the additive shortcut. Make the also the gradient backpropagation is also efficient because it is not going through layers. Yeah. All right. If these are set to 0, the whole block will compute the identity function. I hope that is clear to you. All right. With this, this is the so-called residual. So you can see this one, fx is the residual, right? What is uh, given in addition to x by these two layers. So that's called the residual. That's why these are called resnets, residual networks. A residual network is a stack of many residual blocks. Regular design like VGG, each residual block has two 3 by 3 cons. A network is divided into stages. The first block of each stage halves the resolution with tied to and doubles the number of channels. So you can see uh, here uh, you have the 3 by 3 convolutions and then the so-called skip connection or the residual connection. Another 3 by 3 skip connection residual. So 3 by 3, and after each stage you can see the number of channels here 64 is doubled. This is the thing of the residual network. So they had use the same aggressive stem to as GoogleNet to downsample the input 4 times before applying the residual block to reduce the computation memory requirements and so on. Like GoogleNet, no big fully connected layers. Instead, use the global average pooling uh, and the single linear layer at the end. Okay, so let's look at various versions of the ResNet. So first of all, you have ResNet 18, for example. So stem layer, one convolution layer. Stage 1, two residual blocks, that means 4 convolutions. Stage 2, uh, two residual blocks, that means 4 convolutions and so on. So their so-called top 5 error was 10.92, 1.8 gigaflops. Then ResNet 34, 3 residual blocks, C convolutions, 4 residual blocks like that. They construct a 34 layer one. And then if you just take the VGG16, top 5 error was 9.62, sort of comparable with this, and 13.6 gigaflops. You can see how large VGG is in that context. Then they had this something called bottleneck block. So this is the common residual block. You can see the input is fed to the output directly to add, and they had 3 by 3 convolutions from C to C. 3 by 3 convolutions from C to C. You can see the floating point operations is 9HWC squared, here 9HWC squared. And then they had something called bottleneck residual block here. 3 by 3 C to C here, of course, that's okay. But here they had a 1 by 1 going from 4 channels to C channels, and then C channels to 4C channels again. So because of this, they were able to totally reduce the number of floating point operations drastically. Uh, but to compute this, you have to know that input number of channels you have to fix. So like 256 here, for example, input number of channels, 256. You have to fix. That means here, 4C is 256. Here C is 256. Otherwise, you make a mistake in this calculation. Okay, so here's the simple calculation. Residual, deeper residual module bottleneck. So you can see 256 dimensional here. So that you divide by 4 to make it 64, and then 64, 256, so that you can see you mentioned number of channels, so that you can do this addition operation, right? Okay, so directly from 3 by 3 convolutions with 256 features maps at input and output. So 256 and 256 are 3 by 3, 600,000 using 1 by 1 convolutions. So 256 to 64, the first one by 1 convolution, 64 to 62, 3 by 3 convolutions, 64 to 56, 1 by 1 convolutions, altogether 70,000 compared to 600,000 floating point operation. So you can see it drastically reduces. So with this, we can understand the various configurations of the ResNet. ResNet 18 is like this. You can see we consider this briefly, the stem network, the number of blocks and the number of layers. Each block has 2 layers in the stage 1. 2 blocks, that means 4 layers, 2 blocks are 2 layers. Here, three stage 3 blocks per stage, so therefore 6 convolution layers and so on. So you can see finally you get the number of layers as 34 here. So you can add 6 plus 8 plus 12 plus 6 to understand that how many of them are there. And the stem and the final fully connected layer, giving you 34 layers. And then the 50 layer, so in the 50, ResNet 50, today we will be using ResNet 50. 50 is image net weights. So it uses the so-called bottleneck layer that we studied, the bottleneck. 100 ResNet 101, ResNet 152. These are still very valuable and useful networks. So deep ResNet 101 and 152 models are more accurate, but also more computationally heavy. They are able to train very deep networks. Deep networks do better than shallow networks, as expected. They swept the first place in ILSVRC and COCO 2050 competitions, still widely used today. Yeah. Okay. One of the most cited papers in the world. Yeah. So you can see the number of layers increasing in the ResNet. Then other designs, I will not talk about. So you can study them and then how these things have grown and so on. Group convolutions, squeeze and excitation, network and so on, I will not study. With group convolutions, I have to briefly say something. I'll briefly say something about the group convolutions because it is an important concept. So mm, here you can see the regular bottleneck residual block. So what in the group convolutions, what they do is they will mm, have G parallel pathways. G parallel pathways. So that means they break the number of channels to that many G parallel pathways. That's what the group convolutions are. So here's an example, a group of 2, G is equal to 2. So you can see if you have C in number of channels H times W, and you split it to C in divided by 2 and C in divided by 2. And the computations follow like that. And then finally you concatenate. That is called group convolution. The computational complexity is less because of that. So in very efficient, so-called less heavy networks, they used group convolutions. And then briefly I'll study this depth-wise separable networks. There you can see they use exactly C number of groups equal to the number of channels. Then briefly about neural architecture search. In this, only thing that you need to understand is they used another neural network to find the best uh, choices for building the architecture. Number of filters for the filter height, filter width, stride and stride height, stride width, number of filter, and so on. To find those, they used another neural network, another so-called recurrent neural network to train this network. Then in that process, they found the parameter. So this is called neural architecture search. You search for the neural architecture using a neural network itself. Okay, so if you summarize the convolution neural networks, early work, AlexNet, Zeiler-Fergus network, and VGG show bigger networks are better. GoogleNet, one of the first to focus on efficiency, aggressive step, one by one bottleneck convolution, global average pooling. There's a mistake in these slides. Sorry about that. ResNet showed us how to train extremely deep networks, limited only by the GPU memory, started to show diminishing returns as the network got bigger and bigger. After ResNet, efficient networks became central. How can we improve the accuracy without increasing the complexity? Lots of tiny networks aimed at mobile devices, MobileNet, ShuffleNet, and others. Neural architecture search promises to automate architecture design. So there are these six or efficient nets. So in these efficient nets, what they did was when you double the amount of computational resources that you have, how should you control the uh, so-called depth, width, and the resolution? That for that they came up with some rules. So uh, mm, depth is the depth. You understand? Width is the number of channels actually. By width they call number of channels. Resolution is the spatial size of the images. So they had some rules. So you can see these efficient nets. They are performing very well with very number or low number of parameters. Yeah. I think they used to generate large ones. I think they use neural architecture search. Anyways, these are still available and these are very good networks if you want to use. And then in 2022, they came up with so-called Connex. This is also an important network. We have not studied the transformers. Maybe we will not get time to study the transformers. What they did was they had a very powerful network called Swin Transformer Network, to Swin Tiny and the Swin Base, I think. And they were able to mimic the Swin Transformers performance using convolutions by doing different things. So you can see in blue the next and Swin Transformers performance this much. So you can see they were able to go beyond that performance. Okay. So if you think about what architecture to choose, so we studied a lot about convolution and neural networks. Then if you ask what architecture should I use, so we should not be a hero. This is advice from Justin Johnson. For most problems, we should use an off-the-shelf architecture. We don't try to design our own architecture. If we care about accuracy, we can use ResNet 50, ResNet 101, Efficient Nets B3 to B7, or Connext. They are excellent choices. Efficient Nets combine high accuracy with efficiency through compound scaling, and Connext modifies the CNN to rival the transformers, twin transformer. If you want lightweight, efficient networks, example for mobile or real-time applications, we can use mobile nets, shuffle nets, and efficient nets B0 to B2. That's the summary of this. Yeah. Okay. Any questions up to now? So question is it possible to share one of the past papers? If not, is it possible? Let us know what the exam paper structure will be. So exam paper is an online exam paper. It will be run through Moodle. So therefore, there will be some multiple choice kind of questions and some questions that you have to answer. So I will do something to provide you some information or share some tutorials I have recorded and so on. Yes, I will provide that support. That's the must I have to do. Thank you. Okay. So now we can study a little bit about the backpropagation. But before that, I'll give you a couple of minutes to relax. Okay. So let's go ahead with backpropagation. Uh, this is just to give you an idea about how these actually neural networks work. So we looked at the gradient descent uh, last time. So if you remember, we drew a one-dimensional function like this, one-dimensional function, yeah. And we said that when we take some point along the x-axis called x naught, and if we want to go to the minimum, what we should do? What should we do? We estimate the gradient, and we understand that the gradient is positive here. It's a small angle made with the x-axis. Then we move in the opposite direction of the gradient, that means in the negative direction, and find a new point, x1. And there also, what we do is we estimate the gradient till the gradient is positive and move in the negative direction and so on. So that is gradient descent up until there is no motion. You can apply rules to terminate the gradient descent. But for this, we need the gradient of the function with respect to x in this case. But if you have a function of a function of that means you have these layers and layers of neural networks. You can see finding the gradient of this loss function with respect to this weights is a thing. You have to do it through chain rule. This chain rule computation for a so-called computational graph, which you will see in the slides, uh, can be done by computing the local gradient at that point, and using the so-called gradient that is coming down, which we call the upstream gradient. So this is the thing called backpropagation. This is the main driving force of all the networks now. All the deep neural networks, unless you just use some optimization scheme. Okay, let's look at this. We must define the score function and the loss function. Score function is something like this. If you, from data like images of 768 dimensional images, you come up with a vector of 10 10 if you have 10 classes, that kind of thing. So our image is d-dimensional, and we have n of those images, and that each of these images belong to one of the 10 classes. And perhaps we can have a score function like h equals w2 times uh, ReLU of w and x plus b1 plus b2, something like that. So this is for a fully connected network. It does not matter what the network is. So then we define a loss function, and we studied a couple of loss functions. First one is multi-class SVM loss function. We studied, and we did some manual computations also. So for example, I can give at the exam, I give you, like I did last time, few of those outputs for few of those classes and ask you to compute the SVM loss. Thing like that. Those are the ones. Then softmax loss is like that. You raise to the power e to the power and divide by e to the powers of all across all the classes. So it is like a probability distribution, and then you get the minus log. And this also we did. And then some of those regularization kind of terms are there. But what we need is this: we need to compute the loss functions gradient with respect to W1, W2, B1, and B2. That's what we want. Then we can use a stochastic gradient descent. Why stochastic? Because we use a batch, not all the training examples that we have. So if you have a network like this, 3072 like CFAR10, so this is our D, right? If you have 10 classes, this is our K, right? Okay. So in order to find W1, W2, WB, B1, and B2, we can optimize the loss function. Perhaps if you use SVM, you can use quadrature programming. But in when you have many layers, we use backpropagation to compute the gradients so that we can use stochastic gradient descent. So that is what we are looking at now, how to compute these gradients. Okay. So need for backpropagation, the requirement is to find the parameters W and W2 such that the loss L gets minimized. We use optimization scheme based on the gradient descent. For this, we need gradients with respect to the parameters. So you can see here, with respect to the parameters that we have in the network, we need the gradient of the loss. Of course, they are partial derivatives. So when you consider the partial derivative, you know that we consider all others as constants. Only W2 is a variable. Then we can learn W1, W2, B1, and B2. However, L is a composite function of W1, W2, B1, and B2. So for example, if you take fx equals right x squared, that's not a composite. Not a composite function as such. You can see, you know that the derivative of f x with respect to x, I don't even have to write partial here because it's just a single variable. It's just 2x. But if you have something like this, fx equals sine 3x plus 1 squared, then you can say a composite function, right? You cannot directly compute the gradient. You have to go through the chain rule for that. When you have multiple variables, what is the chain rule? And that's the kind of thing we are looking at now. So computing uh, derivative of L with on paper is tedious. Changes example using softmax instead of SVM loss. Even if it was a small change, you had to recompute the gradient. If you had, you cannot do it on paper. Building a computational graph and using backpropagation can efficiently compute this gradient. This is an important discovery. Okay, so let's first of all look at the chain rule that we have studied when we did gradient or the differentiation in A-levels. Intuitively, the chain rule states that knowing the instantaneous rates of z relative to x and x relative to t allows one to calculate the instantaneous rate of change of w with respect to t. So I'll give you a second to read this part. So look at this now. Our z is a function of x. through f. Z is equal to fx and x is equal to gt. So this is the computational graph. You can see that, right? Yeah. So what is dz by dt? Here, right? Dz by dt is dz by dx, which we can compute from this, and dz by dt, which we can compute from this. And you see that. So this is the chain rule put by George Simmons. The person, if a car travels twice as fast as a bicycle, and the bicycle is 4 times as fast as a walking man, then the car travels 2 times 4 equals 8 times as fast as the man. That is the idea here. Any questions about the chain rule? Yeah. We can quickly apply the chain rule for something. Here maybe let's see Z equals, let's say x squared, x equals uh, 2t plus 1 or something, right? How do you compute the uh, dz by dt? So dz by, well, we have to write partial, dz by dt is equal to dz by dx times dx by dt. Okay, so dz by dx is easy to calculate, right? Dz by dx is 2x. Dz by dx by dt is 2. So you will get 2x times 2, 4x, like that. That's the idea. But not doing on paper like this, but using the computations doing this. All right. But when you have multivariate chain rule, so for example, when you have z is equal to a function of x and y, like so, and then through g and h, this is a function of t, like so, then dz by the partial derivative of z by partial derivative t with respect to t is partial derivative of z by partial derivative z with respect to x and dx by dt. So because x is just a function of one variable t, that's why we can use d. Partial derivative of z with respect to y times dy by dt. So you have to add the individual changes. In the situation, if it is convenient to call z the dependent variable, x and y intermediate variables, and t the independent variables. So like I said, there are many situations for all these things. We can apply the chain rule. Okay, so that is for a simple one. But when you have vectors, what is the situation? Chain rule with vectors. So there are the so-called Jacobian matrices involved. Okay, let's see what that means. So X is a vector of m dimensions. Y is a vector, real, this R means real numbers. Y is a vector of n dimensions. So you can see Y is Y1 to Yn, X is X1 to Xm. Now, all these are real numbers. Jacobian matrix organizes all the partial derivatives of into n by m matrix. So this is the first variable is there of y, second variable is there of x. This is the partial derivative of y1 with respect to x1. This is partial derivative of yn with respect to x1. This is partial derivative with y1 with respect to xm, partial derivative of yn with respect to xm. So all these are there here. So this one is an n by m matrix, n rows and m columns. So Jacobian J is partial derivative of y, partial derivative of yi with respect to xj. is called Jacobian. So a chain rule with the Jacobian matrix. So now when you have y equal y and x, and y is equal to gx and z is equal to fy, yeah. Then when we want to compute the partial derivative z with respect to x, the initial variables with this, then you will have partial derivative of z with respect to yk, partial derivative of yk with respect to xi. So this is the rule, but then you can write that in the Jacobian form. You can write Jacobian transpose partial derivative gradient of z with respect to y, gradient of z with respect to x. So yeah. Thus, the gradient of z with respect to x is the product of the Jacobian matrix and the gradient vector uh, of z with respect to y. So gradient vector z with respect to y can be computed easily. Jacobian is the one that you need to do this. So if you want to implement something like TensorFlow, you can compute these Jacobians and implement, but this is not the way they do it. They have quicker, faster methods of doing that. Yeah. All right. So now we can take a brief example of how to do this. So let's take this computational graph. It's a very simple one. Chain rule backpropagation. So f x y z, x y plus z. So we did that before also. F x y z is q z. We can consider q as x y. So uh, let's take this as q x plus y, and this is z. So now you can see our fxy is now qz because of this choice. So assume that x is -2, y is 5, and z is -4. These are the values of those. And what you want to do is to compute the partial derivative of f with respect to x, partial derivative of f with respect to y, and partial derivative of f with respect to z. These are the ones that we want to compute. So in the forward pass, we can do this, put these numbers -2, 5, and -4. They have been given. Q is, you can see, x plus y. So it's 3. Um, F is q times z, that's -4. -4 times 3, -12. So you can, this is the forward pass. In the backward pass, so we consider, okay, df by d1, df is 1. We consider df by dz. We consider, so df by dz is easy to compute. So f is qz. So although I call it put d, it's a partial. D partial f with respect to z is equal to, so it's partial, no? So you have to consider q as a constant and put q here, right? So this I think you can understand. No? So partial f with respect to q, z, you can understand that. So now if you want to consider partial derivative of f with respect to y, then you have partial derivative f with respect to q, partial derivative of q with respect to y. So partial derivative of q with respect to y is from this, no? Then that is a partial derivative of q with respect to y. Please use the partial derivative sign for this. That's a mistake. So multiply of y is 1, so it's just 1. Okay, let's compute that. Uh, so this is 1, and so with this one, because we have this as q, df by dz, we can put q's value is 3, so that goes there. Then df by dq, we found that df by dq is z, so z's value right now is -4. So for df by dq, we get -4 there. Then df by dy is equal to df by dq times dq by dy. This one we d by dq by dy is equal to 1. So therefore this is df by dq. df by dq is -4. So therefore you'll get -4 there. But this also with this Same formula, minus 4. So you can see how the gradient got back propagated by using our chain rule. But we have to streamline this further or come up with a better algorithmically implemented version of that. That is this one. Now consider this as a node, and if it does some computation, and you have the output variable as Z and the two input variables as X and Y. So a partial derivative of loss function with respect to Z, let's assume that we know that. That came from the right part of the network, or called the upstream gradient. Now, what we want is the partial derivative of Z with respect to X and partial derivative of Z with respect to Y in order to compute the partial derivative of L with respect to X. That's what we actually want. And partial derivative of L with respect to Y. How do we compute that? Partial derivative of Z with respect to X times partial derivative of L with respect to Z, which we have from the upstream gradient, right? These are local gradients. For this function, we have to compute that. So you can see finally, a downstream gradient is equal to local gradient times upstream gradient. This is the rule that is used to uh, find the autograd, automatically do the gradient computation using the computational graph that you design based on the neural network that you want to run. But do we have to do this by ourselves? Absolutely no. PyTorch does that for us. Okay. So let's do one example. Okay, now let's look at this function fxw, yeah, is equal to 1 plus e to the power of minus w naught x naught, w1 x1, and w2. So you can see I have drawn the computational graph. W naught is multiplied by x naught here, and w1 is multiplied by x1 here, and w2 is there here. And what do you have here? W naught x naught, right? You just multiply. Here you have w1 x1. Right. So now in the forward pass, if you assume that this is 2 and this is minus 1, here you will get minus 2 there. And if you assume this is minus 3 and minus 2, it must be given, no? This is 6 there, and this is minus 3. So what do you get here? We have to add these two numbers. And when you add them, you get 4 here. And add these two numbers, minus w minus, and this one, you get 1 there. And then that you have to negate this minus sign is this one multiplied by minus 1, and you get minus 1 there. And raise it to the e to the power. If you raise to e to the power, e to the power of minus 1 is 0.37. You can use the calculator and compute that. And then add 1 to that. To do this is that 1. Add 1 to that, you get 1.37, and then get 1 over. This 1 over thing is this one, and 1 over 1.37 is 0.73. So this is the forward pass through that computational graph. Then we have to do the back propagation. It is easy. So let's consider that the partial derivative of f with respect to f is 1. Then how do we compute this? So 1 over x. What is the local gradient of that? So local gradient, if you consider this 1 over t, so it's 1 over x is like 1 over t, right? I'm using a different variable to show you that it is does not matter, right? Variable name. So 1 over t is derivative, it's 1 over t squared, right? So if you remember that d by dx xn is n minus 1, right? Nx n minus 1. So if you had d by dx, 1 over x, that means x n minus 1, x minus 1, we will have to have minus 1, x minus to the power minus 2, that is minus 1 over x squared, right? This is what we have written here. Okay. So you can see with this one, mm, we can find the downstream gradient because right now this 1.37 is the value of x, so 1 over x. So this local gradient will be minus 1 over 1.37 squared, right? That one you have to multiply with this one. That's what you get as minus 0.53. Okay, so you can see the our rule applied. Downstream gradient is upstream gradient multiplied by local gradient. Computing the local gradient is easy if you know what is that function. So plus 1. What's the local gradient? Just nothing but 1. So you get the same thing there. Local gradient is 1 there. So I should write t here, not x. Then e to the power. What's the thing about e to the power? You get the same thing, right? It's power gradient of e to the power, e to the power uh, x itself. So you will get e to the power t, local gradient e to the power t. So this is minus 1 right now t. So this is e to the power minus 1. So if you multiply 0.53 times minus 0.53 times e to the power minus 1, you will get minus 0.2. And this is multiplying by negative 1. So it's very easy to see that the downstream gradient will be 0.2 because the local gradient is minus 1. Then we have the plus node. Plus node. It is like s plus t. And you can see it's 1. And if you differentiate with respect to t, it is 1. Anyway, so therefore, local gradient is 1. So therefore, the upstream gradient just gets repeated. So also you can see now you can come up with a rule. So if you have a plus node, upstream gradient just get reflected back as the downstream gradient. Yeah. So you can see for each of these nodes, you don't have to do computation, but you can come up with rules. So for many nodes, this is possible. Okay. Now for this node, upstream gradient is 0.2. What should be the downstream gradient? It's a, you can now, you don't have to think about it also. Like it's a plus node, so you get the same thing, 0.2, 0.2. Then what about a multiplication node? So think about the multiplication node. If you think of multiplication node, it's like st, a partial derivative is t, partial derivative with respect to t is s. Now you can see you have to multiply with the opposite term, right? 0.2 has to be multiplied by 2 to get 0.4. This 0.2 has to be multiplied by minus 1 to get this minus 0.2. Yeah. Any questions about this? Yeah, I hope that is clear to you, how to compute do the back propagation by hand. For a simple one like this. This is a computational graph that does not involve vectors. But when it involves vectors, the thing is slightly complicated. Also, you can combine these functions and then treat them as one unit and do that also, but I will not do it now. This is a sigmoid function. Yeah, you can compute it like that also. Computation graph is not unique. We can use primitives that have simpler local gradients. Like so. Okay. So now we have already observed some patterns, and using these patterns, we can just use rules and do that. So for the summation one, you just see the gradient gets reflected here. It's a gradient distributor. Add gate is a gradient distributor. Multiplication grade is a swap multiplier. Swap multiplier, this is the gradient, okay? Red one is a gradient. That gets multiplied by 2 and gets reflected here. It gets multiplied by this number 3 and gets reflected here. It's called a swap multiplier, you can see. Then the copy one, so you have two branches. So for that, if you consider, you will see the gradients get added here. And if you have the max gate or the ReLU, yeah. So here you can see the max gate. Um, so max gate. So let's consider this as X, this as Y, and this as Z, right? Okay. So assume that what you have is max of Z is equal to max of X or Y, no? All right. So consider the case where Y is greater than X. If Y is greater than X, Z is equal to Y. So therefore, partial derivative of Z with respect to Y is 1. So therefore, you can see this one gets repeated. Because Y is greater than X, uh, it does not depend on X anymore, only depends on Y. So therefore, partial derivative of Z with respect to X is 0. Look, it is 0. So therefore, you get 0 there. So yeah, that's the explanation. If you need more explanation, I can give. But otherwise, I think it's generally clear. So, so you can see, you can come up with this rule. So therefore, now if you have this computational graph like that, I can use the forward pass. This is a forward pass, and this is a backward pass. In the forward pass, I use W naught times is X times X naught, and W1 times X1 is S1, right? And then S naught plus S1 is this one, and so on. You can get finally L, right? This is the previous computation graph. So the gradient of FL we consider as 1, and then gradient of S3. S3 is the sigmoid. Sigmoid means 1 minus L times L. So that one we is a rule for the sigmoid. I did not go through it, but it's here. So sigmoid the gradient is like this for the sigmoid. Yeah, so that's what is being used here. And then different kinds of gates, the add gate, the multiply gate, and so on. So with this, we can compute the back propagation of the gradients. So you can see the forward pass and the backward pass can be clearly done if you know the computational graph. Yeah, so I will not go through all these details, but I think you can understand. If you have any question, I can answer. So if I give a back propagation exercise for you, I think you can do that, right? Um, the question was what would the exam look like? So exam would look, maybe I will give you a graph like that and ask you to do a back propagation. Okay. So if you think about this, the implementation of this, you can have the this is the kind of class that we want to implement. So we implemented the last time, whatever the node. So you have the forward for that, not implemented yet, okay, and the backward. Yes. You have to implement. So for example, if you take the actual multiply node, so Python should be implemented in this fashion, right? Multiply node, what is the forward? You take the first input and the second input and multiply, right? That's the multiply node. What is the gradient? Gradient. So you take the upstream gradient, and for the gradient of the input 0, you have to multiply with the input 1's value. Gradient of input 1, you have to multiply the input 0. Remember, it's a swept multiplier, the multiply base. What is the thing about the add one? So, of course, the forward pass is the all the input you should add. and the backward pass the get reflected, right? Upstream gradient gets reflected. So like that, you can implement all these grades, all these different kinds of grades. But these are very simple for the scalars. But when you have vectors and matrices, there are things, so you have to consider them. So I will not go through these things. Other ones like sigmoid one, MLE loss of all these things, you can write these rules. Yeah. So when you think about the autograd function, mm, so class multiply torch autograd function. So static method. So you can see. There's something called context you have to save. So, but this is the x is z is equal to x times y. And in the backward one, context is passed, gradient of z is passed. So you can see this is the gradient of x and gradient of y. And you read. I hope that these are very clear to you. So now you can understand how usually autograd computer like PyTorch or TensorFlow should be implemented to do the backpropagation. So this will not I will not go through many things I wrote, but they are okay, I think. Yeah. So vector derivatives, I will not go through them too much because this is a little bit mind-mongering. But if you like, you can go through them, how to get them using the Jacobian. You have to do local Jacobian matrix. But in reality, they don't use the Jacobian. There is a way to do that. But that way to do that, I will not go through in detail. But the rule is this. If x is I is greater than 0, uh, otherwise. This is how the computer is. This is how the gradients are computed for the element-wise value on a vector. So never we compute the Jacobian. So, uh, so then we have the matrices or tensors, how what that happens. So I think it's too much to think about these things, but if someone is interested, please look at these slides. And if you wish, you can listen to Professor Justin Johnson's lectures. He explains all these things. So matrix multiplication and so on. I will not ask them at the exam how to compute that and so on, how to efficiently think about it, they have given. So you can look at the animations, but I will not go through in detail. But only thing is, without computing Jacobian, there are ways to compute, and these have been implemented in this network. So I have given examples also. When you do matrix multiplication, what you get. Okay. Summary, we looked at backpropagation, chain rule, what is autograd. Downstream gradient in summary is equal to the local gradient times upstream gradient written in this fashion. This is the loss function. Backpropagation with vectors and the Jacobian matrix we briefly understood. Backpropagation with matrix multiplication we did not do. Any questions up to now? Okay, let's take a very brief break and then I will talk about another topic called transfer learning. And then after taking the regular longer break, we will look at object detection. So last time we had a question about how to use things like ResNet. So now we are going to do that. So the idea is this. Now usually these networks have many layers, and then usually they have a fully connected layer at the end that will give us the result. So what we can do is now this assume that this network has been trained on the ImageNet. ImageNet. So multiple times using a lot of computational power, it has been trained. Let's consider this as ResNet 50 or something. So if you put an image like ImageNet something, it will give you the correct class. Car or something, it will give. That's fine. But assume if you want to put different kinds of images to that, like images of movie stars or something, it may not do what you want. So that therefore we have to change the network. But you do not want to train it from scratch. So what we do is we discard this part. We take the same thing here. Okay, now the ImageNet weights are there. We attach this one corresponding to the number of classes that we have. Let's say maybe we have only 4 classes here. With ResNet, how many classes did we have? With ImageNet, you have 1,000 classes. So this fully connected network will give you 1,000 output size being 1,000. So here 4 because we have 4 classes or 3 classes, something like that. Let's call yeah. Actually, in this example that I am doing, only 3 classes. Let me see if I can do 4 classes, 3 classes, and then only train this part. So this is usually called transfer learning. Transfer learning. And then there is another method to do that. That is, you take the full thing and this is called frozen, right? Frozen. So they usually draw a snowflake to show that it's frozen. Snowflake, frozen. Okay, you take this one, and of course you have to add one last layer to represent the 3 classes that we have. And then do not, it's not frozen, it's unfrozen. So you can draw some fire, something, not frozen, unfrozen. What that means is these weights also get changed slightly. So this is called fine tuning. Fine tuning. So this one is, you can say, head only gets changed. Here the full network gets changed. So it is usual to keep the learning rate of this slightly. This one learning rate is smaller than that one because you had to slowly change the weights in the second one. Second one is more powerful than the first one, but it takes longer to fine tune. Yeah. So this is what we are going to study now. We will code. Some parts of the code I will copy because it will take a long time otherwise. But you will get some idea about what we are doing now. So I have it done at home. Actually, create. Okay. But this one I had to create a little data set. So right now I'll show you the data set that I created. So in the code folder, in the data folder, I have a folder called person. In that persons, I created few folders. So for example, I created a folder called, 'Kera', and I downloaded her pictures. And then I created a folder called 'Person'. And then I created a folder called 'Person'. And then I created a folder called 'Kera', and I downloaded her pictures. And then I created a folder called 'Person'. And then I created a folder called 'Kera', and I downloaded her pictures. and folder called Ryan and downloaded pictures, 5 of them. I go to download some more now called Scarlett and have her pictures. And now I will add one more folder. New folder. I'll add one of the greatest actors of all time. Maybe you have not heard of this great man. Him. Um, so I'm going to get some images from the internet of this great human being. Sometimes this is called one shot. This great man, okay. So let's get some pictures of him. I want to get JPG images, JPEG. Right. I don't want to waste time in changing JPG. So I'm going to put that in your folder 2026 code. I have it in data folder persons. Ranjan. Okay, this is the first one. I want to name it as 01 in that folder. Let's take this one. It's a JPG file, yes. I want to name it as 2. Okay, what image do you need? What is? Oh, he's an honorable minister. It's a JPG file, three images. Maybe I need to get about 10, maybe. Oh, this one is 3 images. 4. Good looking images, right? 5. I'm going to get some more. Uh, 6. Are they all JPG files? I want to get only JPG files. They are JPGs. Uh, let's get few more. Few more means like you want to get exactly the same extension. It does not matter, but it's easy then. Oh, it's a J that I don't want. JPG, JPG, JPEG. That renaming is okay for that, I think. I think it's okay. It doesn't matter. Okay. Others you cannot rename like that. Mm. This is him getting arrested, I think. 7. 8. 8. 9. 10. Okay, now I have 10 images of our great man. But now the problem is I don't have 10 images with other classes. I have only 5. Uh, so let's do this data collection. You can see it's hard. So Kera Knightley's images, I have 5. I want to get more. I will get 5 more. This one is okay. It's a JPG, that's okay. This. I have 6. I need 4 more. This one. Maybe I cannot save it as this one. 7. I hope you understand what I'm trying to do. 8. Virus, but the image is not so. Image size does not matter. 9. 1, 10. Let's look at this. Whether the extensions are correct. JPEG, that's not good. JPG, because I want to have all of them as JPGs. JPG, this one is a 1, 2, 3, 4, 5, 6, 7. This is 7. 7, 8, 9, 10. We have 10 there, that's fine. That's okay nicely. And then Anjan Ramanak, we have Ryan Reynolds. So for him, I have 5. I need 5 more. So get some images. Of course, you can save them on your, get them from somewhere. That's also possible. But I want to show you how data set for this can be created also. You have to save them in a fold in different folders, right? And it's okay. Let's see. I think I made a mistake, so maybe I saved it in Keras folder. Uh, yes, you see, I made a mistake, so that is incorrect. I shall put that in Ryan's folder. What persons. 1, 2, 11, 5. This one I will cut and put in Ryan's folder. Okay, 6. 7. 7. 8. I want to get images where only he is there. Otherwise, you can see it's a problem, right? 9. And finalize one more. 10. Okay, so I have cut Ryan's images complete, 10 of them. I want it to be balanced, so that's why I have exactly 10. And then Scarlett's images, I have 5 of them. Get more images of her. Mm, 6. I'm saving them into that folder. 7, because these images are very different. Sometimes it's difficult for the network to correctly classify. 8. 9. Finally. 10. So now you can see I have 10 images of each class. I have 4 classes in this. So these 4 classes, I have them in different folders. Now I want to write the software to use ResNet to be able to classify them by using the ImageNet weights. Some files I need. So I will just put them up until now. We have been using Torch Vision. So those things I will just copy, and the new ones that I need, I will type from Torch Vision, Torch Vision, from Torch Vision, import production.models, import ResNet 50 weights, 50 weights, ResNet 50 weights, Torch Vision. Check here. Okay, so this let's run this and see. All right, so now we want to have the data directory. Data directory is, in my case, the path is, we need a path library for this path. Um, it's in, as you know, dot data person, dot data persons. So from here also you can see that it is so you can see I have data folder and there I have the persons folder. That's where my data directory is. Then I can have the batch size. You know what batch size is. Batch size, how many images do we feed at the same time? So I want to maybe the batch size may be 4. Then number of workers. I don't know what this is too much. So let's go to, it doesn't matter. So please read about it. Epochs for the number of epochs, that's 10. Maybe we can increase that later. Uh, so learning rate for the head, learning rate for the head fine tuning, learning rate for only the head tuning for the first one. That learning rate can be slightly large, that's fine. Learning rate for the full fine tuning, maybe 0.001 or something, a very small one. Then uh, then when you, because you are using ImageNet, there is something called its mean and the standard deviation. So ImageNet mean, so this one, and ImageNet standard deviation, are these numbers correct? 22922, yeah, these are correct, these are well known. And then uh, so the seeding part that we can do in the data transform also we can do. And I will write a function for the evaluating the model. I will write a function for training one epoch, and then I will write a function for uh, the reading from the folder, and then we can train the network, and then we can of course we can transfer that, that means train only the head part, and then we can fine tune, that means train all the parameters in the network with net 50, and then we can compute the numbers accuracies. Yeah. So a little bit of a long code. So first of all, the seeding function, um, set seed. This seed is important because then you can repeat your experiments. Seed. Otherwise, you don't know initially what happens. So because it randomizes the sampling of data points and so on. So random seed, torch manual seed. torch, CUDA, manual seed. Okay, this is correct. Then the evaluate function, def evaluate. I have it written actually, so I'm not just writing by myself. Okay, def evaluate. Evaluator to evaluate, we need to give it the model. We have done that before, and how to load the data, and then criterion. We wrote that last time also, and the device. Uh, this is too much. I will write it myself. So this is model.eval. So and the running loss we need, and running correct. Last time also we did this. That's 0, and the uh, total also we can keep total is 0, so that we can compute the accuracy, right? And then with torch no grad. So for the evaluation part, we don't use the keep the gradients. So no, I don't want this. Uh, so for each image X and label its label Y in loader. So we put them to the device X comma Y equals X dot device, right? X to device. Last time also we did this, and Y to device. That's fine. Now what we do is the outputs. Outputs are logits, logits. We put the X into the model X, and then the loss is the criterion, and output are the logits and the Y. That's fine. And then running loss. Running loss. Uh, you add the loss dot items to the running loss, and then predictions told we can trace first logits dot argmax dimension 1, and then the correct ones, when the prediction is equal to 1, it is correct, and then total, that's fine, and then the average loss, running loss divided by total, and the average accuracy is running correct divided by total. uh, yeah, I think we have to write something like that. If it is 0 greater than 0, else 0, something like this. If total is greater than 0, right? Yeah. Otherwise, you should not put that. Return uh, average loss and running loss. Average loss and accuracy. Return, and then we have to do. Okay. So evaluate function has been written now. Just running selfie. Then we have to write the train one epoch function. So these are important actually. Definition, train one epoch. We have to train one epoch. So for that, we need the model, loader, criterion, optimizer, and device. The whole thing. Model. I don't know how to get one line. Loader, criterion, optimizer, device. Okay. Then this is the model dot train part. Correct. And running loss. Mhm. Yes, running loss and running correct and total. Then for each we have to do this for image is X, Y is the label in loader, mm, X comma Y equals X2 device and Y2 device. Put them in the CPU or the GPU depending on what our device is. Okay, device. Then, of course, now this is a training. We have to zero the gradients. Optimizer, optimizer zero, Brad. That's correct. And we have to compute the logits, that's model X. And then we have to compute the loss from the criterion. And then we have to do loss backward as we did last time. And then after that, loss step. So this is the gradient descent step. And then these are okay, running loss prediction, logits arguments 1 and running correct predictions equals X is correct and then total and the average loss we can compute and we can return that. That's correct. Let's see whether everything is correct there. Okay. Uh, then for the reading, we can define a function to see whether they are JPEGs. Def is valid image um, to see if it is a JPG file or some other file name, what we are only considering JPG files. So, so uh, return path, path. See whether this path is on for JPGs. Suffix lower. So we can mm, put other ones also, but we just have JPG file. So this is enough for us now. You can see the other parts. It prompted us to put other file extensions also. Then we have to do the splitting. In the splitting, we have 10 images and we can split to training and validation set, and these things are required, and the transforming part is required because we have to change the images to 224 by 224 because the ResNet image size that they use is 224 by 224, and then we can actually start the training. So a little bit more code to be written to come up to that stage. Uh, so this function is build uh, balance split indices. Data set and the uh, image folder data set and seed also. This seed is important because we don't want to get different splits so that we don't know what's happening with our training when we want to debug them. First of all, we can pick two validation images from each class. Mhm. So 10 classes, 10 images are there in each class. Um, Random number generator, random random seed, and then class 2 indices is 0, class 2 indices. Then this is correct for index label enumerate image folder dataset. Mm, right. Dot sample. Mm. Last indices set default label appendix. This is also correct. Then train indices. Train indices nothing. Oh, validation indices nothing. For CLS IDs, uh, indexes in class 2 indices items, that's correct. Random number generator shuffle, if yeah, let's manually write it. If len, let's some, this is just to do some checks. If less than 2, then we don't have enough too few images, right? Uh, return value error has less than 2 samples, cannot create balance. That's okay. Yeah. Validation split indices divide the val indices append. Let's 0 first get the for the validation, let's get two of them. 0 and 0 to 2, 2 for validation, and for training indices 2 and others. Okay. So this done. So return train indices, validation indices. So you can see we take out of those 10 images, we take 2 as validation indices and rest as training indices. Okay, that's fine. Set seed, seed. We define the seed at the top. How did we don't define seed at the top? Okay, we did not define seed at the top. Set seed 42. Okay, then device. Remember this torch device, CodeIF torch is available as CPU. We have that using device. We also print that. If not data directory is not does not exist, file not found, something we will type. And then this is the most important line, weights. Weights equals ResNet 50 weights. Uh, we are getting the ImageNet weights. ImageNet V2. I don't remember this part, this V2 is, so you can find out on you. Then we have to transform, remember the transform the images, transform compose. This is important. Transform random resized. Transforms dot random resize crop. So resize and get a crop of 224. 224 2 to 4, and scale, let's say 0.7, scale to point 7, and 1. So with these scales, they will scale and pick, crop it and pick. So this is you can generate more images. Is there a problem here? Okay, let's take that whatever. That's okay. Then we have to flipping, transform horizontally. That's correct. Then random horizontal flip, which maybe you can with probability 0.5. You can see we are generating more data from what we have by flipping. That's one of them. Affine transformation, affine, random affine, random affine. So you can give the degrees, the translation, and scale, and so on. So you can see with this we can generate more data. Transform color jitter, brightness, contrast, and all those things we can change. And then finally transform to tensor, and then the transform normalize, weights, image net mean, and image net standard deviation. So we have defined that. Where is it? Image net mean, image net std. Image net std. So okay, that's a transformation function that is done. This is the transformation for the training. So well transformations, transform. So resize to maybe 256 by 256. Oh no, we did not write 256. 256 comma 256. I hope with all this big code I'll be able to get it working. And then transform center crop. So crop the center to at the center 224, and transform to tensor image net. Yeah, okay, that's also correct, I think. Now, our data set is in the folder. Now we have to uh, full force split. So data sets image folder, and we have to give the data directory, and data sets dot image folder, and then we have to give the data directory root str and our data directory, and transforms. Let's do the transforms later. Is valid file. Yeah. Okay, that's correct. So then class names, number of classes, class names dot length, print classes, maybe print classes, class names that perform the folders, and number of classes we can print total number of images found. Okay. All right. Oh, Here, unexpected argument P. P.5, random affine. Okay, probability is not there. Yeah, okay, total number of images found is 40, that's correct. Classes is 4. Kara Ryan, okay, that part is okay. Is good. So, then train indices from train indices, valid indices. Okay, so now we wrote that function, so we are getting that. Then train data set. Data sets, image folder. Okay, that's good. Then train validation base. Yeah, these are the base images that we have read. Now we have to apply these transformations. Subset. Okay. Now loader, data loader, train data set, batch size is batch size, shuffle is true. Yeah, okay. Then the ResNet part. So maybe you can print the train samples. Yeah, okay. Validation samples. Now we can start the ResNet 50. Model, because models ResNet 50 weights. Weight. So we have written what the weights are. Those are ImageNet weights. And then in feature, this is very important. In features, model FC in feature. So for the fully connected layer, these in features. Model FC, now we are giving, you can see a new uh, layer, a linear layer with number of classes. Our number of classes is 4. The layer that we took off would have been 1000 classes. So model to device, that's correct. Criterion cross entropy loss, that's okay. Then validation loss before any fine tuning. Validation accuracy before. So evaluate the model with the validation loader criterion device, and we can print the validation and validation accuracy beforehand. So this is without any fine tuning. So you can see, oh, it's downloading the weights, downloading the ResNet weights. That's why what's downloading. Oh, error. That I don't know how to find. Model. Look at the train loader. At the loader. Train loader is the problem. Data loader. DA. Batch size. Shuffle is true. Validation loader. Yeah. Control one. Validation. Yeah, maybe after the break I can correct. Validation. Validation sample says 22228. Yeah. I'll do a brief check and take a break. Maybe we can take a break while I check this. Yeah, you can go for the break. We'll meet at 11 10 or so, 11:10. No? I'll stop post. Okay, the mistake that we had was when I said the indices, I made a mistake. So now that I have corrected that, now the code is working. So the important parts of the code are the loading of the RESTnet with the ImageNet weights. These weights, RESTnet weights, ImageNet 1000 V2. Yeah, and then after that you can see input features to the last layer are these. And then we replace this fully connected layer with a linear layer with these input features, and then the number of classes that we want, which in our case is four, because we had four celebrities. And then model 2 device, and then cross entropy loss. And if you just check the validation loss below, it is very high and the accuracy is 0. And then you can see for the head only training, we require that we say false, and then require grad true for only the fully connected layer. And then we uh, run it for that many epochs. Then we have the fine tuning. Then you can see we are say require grad for all the layers. And then we train for that many epochs. And you can see the when we do the only the head training, that is transfer learning, we get a validation accuracy of 0.62. When it is more than 0.25, because we have four classes, 0.25 is the random thing. If it is 0.62, it's good. And then we start fine tuning, and we got 0.75 validation accuracy. And we had little code to be able to give an image from that fold and test. And you can see it is producing correct results. The problem that we for all the images that it loads is predicting correctly. So that's the problem I had. It should make some mistakes for some of those validation ones. So maybe at home you should add some more images and try to test it to see whether it makes mistakes. Yes. Okay, thank you. So I have uploaded this file to your Moodle along with the images. Now we want to briefly look at object detection. Uh, Actually, I want one more class. Let's see whether I can get that arranged. But if you do not have time at all, then I can just record it and put or something, because as you know that this is not for the examination. We are doing this. We are doing this to understand uh, how to do the computer vision part. So therefore, we need to understand transformers. Maybe I will not be able to complete the object detection today. And then we need to, I wanted to talk about some new things also in the computer vision field, image generation, diffusion models, and so on. Okay, object detection is an important thing. So I'll briefly tell you what object detection is, and then talk about your work. So see, is there any question before that? Go on with that. Okay. Assume that we take an image of a kitten or something, and we run a CNN like the AlexNet that we have done, and we get a 4096 feature vector, and then we fully connect it to 1000, and then we will have probabilities for the 1000 classes. So hopefully the correct class will have high probability, right? That's what the classification means. And it is a probability for each class. So in our example that we give also for each of the images that we give, it gives you a probability. But there are other vision tasks other than the classification. So giving a label per image is called a classification. There's no spatial extent considered. But semantic segmentation means so for each pixel, you give a label of a class and grass label, cat label, tree label, sky label. So this color, there's a problem. And so on. So no object, just pixels. So it just classifies the pixels. It doesn't have the notion of an object. But object detection means you identify the class as well as you draw boundings for box for the class that is in that bounding box. You give it a name, right? Dog, dog, cat, as you can see. But instance segmentation is more superior than that. So you classify individual pixels and also you give it a class name. So you can see there are two dogs here, right? This dog and that dog. It individually identifies those dogs and the cat. You can see. Yes. All right. So object detection task definition is a single RGB image is given. A set of detector objects must be output. For each object, we must predict a category label from a fixed set of known labels, cat, dog, and so on. For image, it's 1,000. For our example, it's 4. And bounding box numbers must be given 4 numbers because we need this corner and that corner, right? You can say xy, x1, y1, x2, y2, or center xy and the width and the height. Both are okay. But usually center and the width and height are the numbers that they use. So the challenge is no need to output multiple outputs. No need to output variable number of objects per image. Need to output, right? That is the problem. So multiple types of outputs need to predict what the category label as well as where the bounding box. Large images classification networks at 224 by 224 as we saw. Here we need large high resolution images. Okay. Uh, By the way, a question for you. In the previous example that we did, we had various sizes of images, right? Why did this network work still? Because ImageNet is trained for 224 by 220. The answer is in our transform function that we wrote, we resize it to uh, resize it to 224 by 220. So question, what is then YOLO for classification? Actually, YOLO is for object detection, not for classification. Other than YOLO, there are other models like PointNet, CenterNet, and so on. But because the YOLO is now run by a company called Ultralytics, and they have incorporated all these advancements in other networks also to that. So YOLO is the thing to do for image classification, image object detection. Yeah. Okay, so now let's look at detecting a single object. So here you can see a cat. So single object detection means we want to not only call it the cat image, but we want to draw the bounding box also like so. So treats localization as a regression problem in this case. That means we want to find these numbers, these four corners, or the center and the height and the width. So you can see these are not class labels, but these are actually real numbers, four real numbers. So we call them regression, right? So often pre-trained on ImageNet. So now I hope you understand what this is and transfer learning. CNN features computation example using AlexNet. So you get vector of 4096. From that vector, we have to get it to a fully connected 1,000 because there are 1,000 classes, and we give the class code cat so on and so forth using the softmax and correct label can be found. And in addition, we have to connect it to 4096 to 4. Each of these four will give you x, y, width and height, and with an L2 loss. That means you square them and x minus x prime square. Because you have the correct ground truth. So ground truth boundary boxes must be there. Then you can regress and get the network to predict the bounding box also. So you can see treating the localization as a regression problem in this case. Okay. Now you think we have solved the object detection problem. Actually, we have not. Anyways, when you think about the loss, they use both these locks, the bounding box loss as well as the softmax loss classification to get the so-called multitask loss. So it is common practice to combine different kinds of losses as a multi-class loss in multitask loss to get these networks working. So the problem is images can have more than one object. That is a problem. So you can see in this case, to detect a cat, you can see we have no problem. We can say cat and X, Y, WH. We need to just predict four numbers. Here you can see there are three, we don't call them object, three animals, two dogs and a cat. So we say dog and the bounding box, dog and the bounding box, cat and the bounding box. And therefore we have to give 12 numbers. But if you take this image, there's so many ducks, the small ducks and the big ducks, duck, 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 and so on. For each of them, we have to predict the bounding box. So you see, the number of outputs that the network should have is not defined. It changes depending on the image. And this kind of thing we cannot do. Need different number of outputs per image. This is a problem if we adapt this paradigm for object detection. So detecting multiple objects in sliding window fashion. So you put the sliding window here, and at each of these boxes, we see whether there's an object. Apply a CNN to many different crops of image. CNN classifies each crop as a object or background. This is possible. But the problem is like how many bounding boxes should you check? How many possible boxes are there in an image of size H and W? Let's consider this. Consider box of size H, small h and small w. Possible locations are w minus w plus 1, h minus h plus 1. Those are the possible locations now. To keep that bounding box, keep that bounding box of size w and h. We can keep it everywhere in the image, right? Anywhere in the image. So therefore, the possible positions are there, and then sizes are also different. So total possible boxes is like this, and this is not handleable. 800 for an 800 times 600 image, it has 58 million boxes. No way we can evaluate them all. So this is not possible. So therefore, people had to come up with something called, they came up with a solution called region proposals. They used some network that is not actually deep learning based, but a classical network to give us the possible boxes in the image. They do some objectness tests. And this is done by something called selective search. It's a very famous paper. Find a small set of boxes that are likely to cover all objects, often based on heuristics like look for blob-like image regions. Relatively fast to run, selective search gives 2000 region proposals in a few seconds on a CPU. So we can see these are these candidates, object candidates, you can say. So then we use each of these candidates and run them through a CNN to find if that is actually an object. And if that is an object, what is the actual class? This is the object detection uh, pipeline that the people have adapted in the so-called two-stage detectors. Not one of them. We will evaluate later. Okay. This is the first contribution in 2015 called RCNN. It's a very famous paper. Region proposes plus CNN features due to Ross Gershik and others. You can see the input image and then you locate the 2000 region proposals that came out of this selective search. And now each of these, we walk to a certain size, like usually 224 by 224, and each of them we run the convolutional neural network as we ran our SZ50 on the images. So forward each region through the CN component, and then for each of these outputs, we run a support vector machine to classify, and we do the bounding box regression. Classify the regions with SVN and bounding box regression to predict the transform to correct the region of interest with four numbers. TXTY, THTW. So, but there are some things that they do for this before regression, the transformation. We will not worry about it. But I think you understand the thing with the RCN. Problem with RCN is for each of these 2000 locations, for each of these are they have shared only through three here, but there can be uh, uh, 2000 of them. For each of them, you have to run them through the convolutional neural network. So each image, you have to run 2000 convolutional neural networks. This is actually very expensive. Yeah. So for a single RGB image, what do you do? Run the region proposal method to compute the 2000 region proposals, resize each region to 224 by 224 and run independently through the CNN, like so. Uses scores to select the subset of region proposals to output. Many choices are there. A threshold on background or per category, or top K proposals per image. Compare with the ground truth boxes. Okay, then we need to also understand how do we measure the goodness of object detection. When you measure the goodness of object detection, we have to see our detection box, how our detection box, the prediction overlaps with the ground truth box. So you can see here the prediction box in light blue, assume that this is what the network gave us, and we can see in the green border the ground truth box. That is some person annotated that. So there is this overlap, right? This overlap. When this overlap is large, it's better, right? So you can see the area of intersection, this one, divided by the area of the union. This is the metric that people use. This one is called IOU, or intersection or union. There's another one called Jackass similarity. Jackass similarity we will not consider, but especially in biomedical image segmentation, they use. IOU greater than 0.5 is great. Greater than 0.7 is very good, and greater than 0.9 is almost perfect. Yeah, this is good, but when you have overlapping boxes, what do we do? I'll give a second to think about it. Now you can see, now for this each dog, there are two boxes, right? What is the correct one? How do you do that? I'll give you a second to think about a way of doing that. Yeah, okay. I'll give you the algorithm. Problem is often detectors output many overlapping detections. So for that, we have to apply the so-called non-maximal suppression. Non-maximal suppression. Solution is post-process row detections using non-max suppression. The algorithm is this: select the next highest scoring box. So then select next highest scoring box in this case is 0.9 box. That's the green box. Eliminate lower scoring boxes with threshold greater than 0.7. Threshold greater IOE threshold. So now here the overlap of the blue box with the green box is very high, right? Yeah, it's very high. Overlap is very high. So therefore, because that is very high, because we have already selected the box of this dog, we can eliminate the blue one. Then pick the next large one. Next large one is 0.775. With 0.75, are there overlaps? Like that we consider. So for example, IOU, intersection over union, between the green one and the blue one is 0.78. Green one and the orange one is 0.05. Green one and the light blue one is 0.07. So therefore, we eliminate that 0.78 box. Yeah, like so. Then we take the orange box. With that, the blue one overlap is 0.74. Others do not overlap that much. So remove that blue one. Yeah. So you can see this the value of maximum separation. When more than one box is detected per object, it has the power to remove. Okay. But overline boxes non-maximum separation does not work when you have large number of objects. Anyways, may eliminate many good boxes when objects are highly overlapping. So there's no good solution for that. Okay. Then there is a thing called mean average precision. I will not talk about this too much, but only tell you, mm, only tell you one step here. So now think about this: all dog detection sorted by score. Okay, here assume that we are detecting dog objects. All dog scores like point. There's dog 0.99, 0.95, 0.90. 0.5, and 0.10. These are all ground truth dog boxes. So all the ground truth dog boxes must be selected now. Yeah. So if uh, let's do this now. Uh, so now there's a match between this. IOU is greater than 0.5. So that means uh, we have detected one dog with 0.99 precision thing here. That is correct. So that means precision is 1/1. Out of the one that we detected, it is correct. Precision is 1/1. Recall means, but out of the three actual boxes that are there are dogs in the image, still we have detected only one. So the recall is 0.33. So we plot a point here. 0.33 recall, precision is 1. Right? Then get the next one. That's okay. The next one, there's a match greater than 0.5. And then you can see out of the two that we have detected 0.99 and 0.99, both are correct. Both have round truth matches. So precision is 2 divided by 2, 1. Recall, now we have covered two round truth boxes, 0.667. So we have one more dot here. Okay. So for the 0.9, no match with ground truth. So therefore, our precision is low. As our precision is now 0.2/3. Out of the three that we detected, only two are correct. So recall, now still out of these three, we have two dogs covered. So like that, you can see we plot this so-called precision recall curve, and area under that is called dog average precision, dog AP. But this one we had to do for all the classes, dog class, cat class, so on. And then when you do that, we call it mean average precision, or we call it MAP. MAP, mean average precision. So that is what the object detectors report. So there are some caveats. So because we have taken MIA IOU greater than 0.5 as a correct detection, right? But some people will have stringent standards. Some may say, okay, we have to go for a higher IOU. So therefore, that's why some they like at 0.5 and so on. So at 0.5 IOU. Yes. Yeah. So for Coco, this very famous data set called MS Coco, they define Coco MAP. So they have multiple thresholds, and they do multiple thresholds and find an average. This is that's the Coco MAP. So I think now you understand how to measure object detectors, and we understood what RCNN means. Okay, the problem with RCNN is every single region proposal had to be forward passed through the convolutional neural network. 2000 convolutional neural network passes, that is very slow. So then people thought what to do. So the solution is to switch these two. That means run the convolutional neural network once on the image, and from the output, map the region proposals to those and extract the features. Yeah. So you can see this is the RCNN. Fast RCNN means run the convolutional neural network first, and then features of the fifth convolutional layer something, and then on top of the region proposals, of course, you have to adjust the sizes, and out of that extract the features, and in those on those run a very small CNN to get the class as well as the bounding box regression. I hope it is okay. This is called fast RCNN. Mhm. So you can see here, backbone network, we can have VGG, AlexNet or ResNet. Regions of interest ROIs have been located from the region proposal network on the fifth convolutional map, and you take those features and run through a per region small neural network. So this convolutional neural network is quite small. From those outputs, you classify them and build the bounding box. Yeah. So per region network is relatively lightweight. Most of the computation happens in the backbone network. This saves work for overlapping region proposals. So example, when we using AlexNet for the detection, 5 layers are used for backbone and 2 fully connected layers are used for per region. Next slide. Yeah. Or ResNet also we can use. So if you are using ResNet, you can use up to some extent to the ResNet. Yeah. Okay. For this, you can see the region of interest. For these features must be extracted. So we run the convolutional neural network, and then there are the features, and then we project the region proposals onto the network. And then now you can see that the region of proposals do not exactly overlap with the boundaries of the image feature map. See, image feature map, the feature is this, but it is not mapping the region proposal is not exactly mapping. So then you have to do some snap to grids thing. So you snap them and then divide it to 2 by 2 roughly equal subregions, and then max pools within those each subregion. So this is called ROI pool. Region features always the same size, even if input regions have different sizes. So this is an advantage in this case. So, but it has other problems also. Problem, a slight misalignment due to snapping different size subregions is weird. So those two problems are there. So a little bit of illustration of the ROI pooling, you can see uh, the region proposals be located and then divided and then extracting the max pool values, maximum values from those. Yeah, it's ROI pooling. So then there's a thing called ROI align that we will not talk about too much. So this is interpolation based method. This is more advanced. Yeah. So fast RCNN versus slow RCNN. Now you can see we studied this. So this is what we studied. So from the this the RCNN, we have switched the region proposal and this one. So we can see the comparison between them. Okay, so I will take 1 or 2 minutes again. Now they observed again. So now the observation on the RCN was because of the region proposals network, it took so much time. And then fast RCN is test training time is very less, 8.75. But testing time, when you compare, RCNN had that many seconds testing time, 49 including region proposals, and this is not different. So region running region proposal is no problem for RCNN. But if you think about fast RCNN, region proposal time was 2.3 seconds, but excluding region proposals is 0.32 seconds. Now you can see the proportion of time taken by the region proposal is huge. So therefore, people wanted to get rid of this region proposals network. Problem runtime dominated by the region proposal. We call region proposals computes by heuristic selective search algorithm that runs on the CPU. So CPU algorithms are slow. So you want to go for a GPU algorithm in the graphics processing unit. In the training that we today also we selected the device, if you remember. So there what they did was on the feature map that is computed using the CNN, they ran a so-called another network called region proposal network. So no more selective search. And here classification loss and the bounding box regression loss uh, can be done on the region proposals. And so there's a different this different recipe of training that maybe I will not talk about that too much. This one is called an RPN, region proposal network. That is what came in the faster RCNN. Uh, so uh, uh, I will stop right now. Maybe talk about YOLO when if I get time. So I will ask the coordinators whether I can get another class. If not, maybe I can record something and put because understanding YOLO is also important. Okay. So that's it for the time being today. So if you have any questions, you are most welcome to ask. Otherwise, we will stop for now. Thank you very much for joining. Please do the quiz and please do the little exercises that we did in class, coding exercises. I will stop the recording.